Okay, so this is a very useful technique, right? But it's not actually going to be applicable to all distributions. So it's good for what I can call finite distributions, which means the probability of a random variable less than a certain value or greater than a certain value is always 0, like uniform distribution or triangular distribution. It doesn't really work. It doesn't really work, at least naively, but for infinite distributions, such as exponential distributions, right? An exponential distribution has a PDF of x that is proportional to e to the minus lambda x, right? And for this to integrate to 1, we need have a 1 over lambda. So this is for x greater than 0. So this is what an exponential distribution is like. And for example, in physics, the decay of a radioactive element, the time to the next alpha particle, for example, coming out, is pretty much an exponential distribution. Okay, and essentially, this is saying that the x is more likely when x is small, but as x goes larger and larger, there will never be a cutoff, right? I mean, it's much less likely that x is large, but you will never have a 0 probability. The probability is always there, no matter how big x is. So this kind of infinite distribution with a tail doesn't really work with our acceptance rejection method, because you are required to construct a uniform distribution that covers the entire range, and you cannot have a uniform distribution that covers from 0 to infinity, can you? So we need another method, okay, to sample distributions that are like infinite. Another example is the Gaussian distribution or uniform distribution. Okay, so how do we do that? So I'm going to be introducing another method that is used to sample infinite distributions, and I'm going to be using exponential distributions as an example. So the PDF is equal to, again, 1 over lambda times e to the minus lambda x if x is greater than 0, or 0 when x is less than 0, right? So if you draw it, PDF, it behaves like that. So if this is 0, it's 0 here, and then it's like that, right? So the value here is 1 over lambda, and this is x. Okay, so this method I'm going to introduce here is called the Inverse Cdf method. And instead of focusing on the PDF as in our acceptance rejection method, we want to focus on the CDF. So the CDF of the exponential distribution is the integral of the PDF. So if you integrate it, right, you're going to see again it's equal to 0 when x less than 0. But when x is greater than 0, it is actually 1 minus, right, exponential of minus lambda x for x greater than 0. I mean, the integral basically absorbs this. Wait, I think I made the mistake. The PDF is a derivative of the CDF, so this is actually not 1 over lambda, but actually lambda. in order for the integral to be 1. So this is the lambda, and the PDF is actually lambda. Right. Okay, so yeah, so this way, when you differentiate the CDF, minus lambda comes out, the minus sign cancels, and you have a lambda times e to the minus lambda x, right? Okay. So if you draw the CDF, what it looks like, of course, it asymptotes to 1 as x goes to infinity, and it stays 0 when x is negative, and then it goes like exponential to 1. That's what the CDF is.